All right, so this is going to be the first video in the FERP video key video set. I'm going to just go through each section as a separate video to break it down, and so that it's not 45 to 50 minutes long as a whole, and you have to siphon through the video to find what you need or what you want help with. So this first part is going to be all about the moles. I'm not going to go through the definitions here. Those are on the regular key, but you can also Google or go back in notes and kind of get those definitions for those items up there. But I'll start at number 1, and then we'll go through the moles section. Write the formulas for the following compounds. They are all ionic compounds because they are all starting with metals. Manganese is a transition metal, and remember those Roman numerals tell us the charge of that particular ion for that metal. So potassium's a +1 charge, and iodine is a -1. So you crisscross those charges and you get just Ki, and you only need one of each to balance out. And remember, the charge total has to equal 0. They have to cancel each other out. Manganese here has a +4 charge, where phosphate, remember our 8s and ites are on the back side, and that's a -3 charge. So you crisscross those and you end up with needing 3 manganese +4 ions and 4 phosphate ions there. So that would be your total amount of each of those ions. Calcium is a +2. Phosphide, remember anything "ide" except like hydroxide or cyanide, are found on the front of the periodic table. You just change those there and you switch them, all right? So you have to make sure you know how to crisscross those charges to create your ionic compound formula. Write the compound name. This is strontium, and since chlorine is by itself, we just change the ending to "ide" there. Lithium, and it is attached to a sulfate polyatomic group. You can tell because there's 1, 2, 3 elements as opposed to 2 there, which tells you that something in there is on the back side of your periodic table in that polyatomic ion chart. And then over here we have lead, and now lead is a transition metal, so we're going to need a charge in Roman numerals here. Well, there's only 1 lead, and there's 1 carbonate ion that it's attached to, and since carbonate's a -2, that must mean that this lead ion is the +2 version of it. So we can put 2 there. And note that that's not 2 as in there's 2 of them, right? It's 2 as in that's the charge on that lead ion. Balance the following equation. This happens to be an acid and a base, and that's kind of fresh in our minds right now. But whenever you have an acid and a base, you see that or hydrogen and hydroxide are separate because that's what makes the acid, the base, the base, which means that I'm going to take water, and I'm actually just going to rewrite it as HOH. And now that's because that'll help me balance the H in the front with the acids hydrogen, and then the OH in the back with the base OH, right? So that's kind of why we do that. So it makes it a little bit easier. Here we have we can start wherever we want. You can put a 3 over here. You're gonna end up having to change that here a little bit because of this substance right here. You see that there's 3 magnesium. So why not make that change first? And that gives us 3 magnesium over here if we put a 3 in front. And that also gives me now 6 hydroxides, right? 6 hydroxides, which means that over here I would need 6 in front of the H2O or the HOH, whatever you want to write it as. And that gives me the 6 hydroxides there, and it also gives me the 6 hydrogen in the front. And I have a 2 out in front now over here because that'll give me the 6 hydrogen I need there, just always multiplying the coefficient by the subscript for the total amount of that particular substance. And then, of course, we didn't have to do anything there, so you can leave it blank, or it is a 1. Predict the products. Be sure your formulas are correct. And this one's weird because iron's a transition. You're like, well, what is it choosing? +2 or +3? Since we don't specify, let's go with the nicer one for this case because SO4 is a -2. We'll just say that this was a +2 iron ion. So with that being the case, this is a single replacement reaction, right? So iron comes in and it kicks copper out and takes its place. So that is iron. And if it is a +2 charge, sorry if you hear something in the background, that's the dog that wants to go absolutely bananas right now. So those cancel each other out. And we see that since everything has a 2 charge one way or another, then it is already balanced. So we are all good to go there. Over here, this is a neutralization reaction, which is basically a double replacement reaction, right? Because it's an acid with a base, which means that we're going to always end up with water as a product, which is liquid. And we're going to end up with a potassium sulfate, salt. And we call it an ionic compound a salt. All right, so we have +1, -2. You crisscross those. I'm going to need 2 of those potassium ions there to balance out the 1 sulfate ion. So you see we have to balance our charges before we move on. Everything is going to be aqueous there. Over here, when the metal is by itself, you can assume, unless it's mercury, that it is solid. And we'll say that this will be aqueous as well, right? States of matter are important. That you will be given answer choices that have the states of matter on them. Using factor label, dimensional analysis, right, or factor label, just creating our T charts or tables or however you like to do it, just fractions. So we're just using these conversion factors up here. We have 4,580 hours, and we want to go to years. So I like to do the table just to keep things a little organized. I know some like to do something like this and then keep it going like that. It does not matter one bit, whatever you feel comfortable with. So hours are on top, which means hours need to go here to cancel out. And I can't go directly to, you could in theory, but because based off of the conversion factors I have, instead of going from hours straight to years, I can go from hours, which is 24 hours, to days, right? And then from there, I can then cancel out days down here, and I know that there are 365 days in 1 year. Right, so we cross out those units. We end on top with the unit that we want, and our answer here, if I'm not mistaken, should be somewhere on this sheet, and it's not. So hey, why don't I calculate it right now? So let's open up the calculator. We get we get 4,580 divided by 24, and then divided by 365. Remember, everything that's on the bottom gets divided. Everything that's on top multiplies. And we end up with whatever this is, right? 0.52, right? So that's 0.52 years. Right there for 4,580 hours. And we do the same thing with 29.6 days. And I'm going to minutes. I know that there are, we'll go straight from days to hours. So 1 day has 24 hours. And how you abbreviate these is up to you. But hours will go here to cancel out. I know that in 1 hour there are 60 minutes, right? So that's how we use those conversion factors. Everything cancels out except what we want, right? And then we go and answer that. And of course, make sure that the proper units are there. So 29.6 times 24 this time because it's on the top, and times 60 because it's on the top. That would be 42. Hello. There we go. All right, make that a little bit nicer. Going a little too quick. 42,624 minutes are in 29.6 days. So we use this idea of dimensional analysis when we go through stoichiometry or mole calculations such as this. Whenever you see molar mass, all we have to do is take the substance that we're given. In this case, it's potassium, and nitride means that it's nitrogen by itself. And those are the charges. So if you crisscross them, I know that I have a formula of K3N, and I know that I need to find the mass of potassium, which is 39.10, and the mass of 14.01 for nitrogen. And then because I have 3 potassium, I am going to multiply that mass by 3, right? Because we have to account for each one. It's like going shopping. If you buy 3 items of the same thing, you have to pay for all of them. So this ends up being, I believe, when you add these together, 131.31 grams of K3N. All right, and what we can do with that, and actually, I'm sorry, that should be grams per mole. Grams per mole of K3N, because grams per mole is molar mass. That's why we can use it to go back and forth between these units, right? Grams to moles, moles to grams, and so on and so forth. So let's calculate the molar mass of lead 2 phosphate here. Lead 2 tells me that's a charge of +2, and phosphate is a -3, so you're going to crisscross those values, and you get PB3, and because I need more than 1, I'd have parentheses there. So here's the list of all of the elements that are a part of this. You have to add the masses or contribute those masses individually. Lead has a mass of 207.20. There are 3 of them, so I multiply that by 3. Phosphorus, in each individual PO4 group, there's only 1, but because there's 2 of them, that's kind of like writing PO4 2 times, right? And that shows us that we have 2 phosphorus atoms that we have to take into account. So multiply that by 2, and then you do the same thing. You see that oxygen 16, and there are 8 of them. 4 times 2 is 8. And once you add all of that up, you end up with, I believe, 811.54 grams per mole there for lead 2 phosphate. So now we're going to calculate the mass of this many moles of sodium nitride. And again, sodium nitride is Na3N because of the charges. And before I move on, I need to make sure I calculate the molar mass as I did above. So there's a sodium, which is 22.99. There is a nitrogen, which is 14.01. There's 3 sodium ions, so I have to do that. And I end up with, once I add them together, 82.98 grams per mole. Now, because I have this value, what I can do is take that value that I'm provided in moles of Na3N, and I can use that to then cancel and get rid of moles as a unit and go to grams. So moles of Na3N to grams of Na3N. And again, this value is just that number of grams equal to 1 mole. No different than up here, how 1 hour is equal to 60 minutes, or 1 minute is equal to 60 seconds, right? We use that conversion any way that we need to. In this case, since moles are on the bottom, the 1 mole goes there, and the 82.98 grams go on the top. Mole as a unit will cancel out for you, as you see, and you get an answer of 379.47 grams of Na3N. All right. How many liters are in this many moles of neon at STP? Now, at STP, we know what that means since we did our gas laws unit. Remember, STP is standard temperature and pressure, right? That's all that means. And what that tells us in a problem like this is that we can use the fact that 22.4 liters at standard temperature and pressure are equal to 1 mole, all right? So that's a conversion factor. So that's all that lets us know, is this conversion factor right here. So how many liters are there? Well, I can go from moles directly to liters because I have that conversion factor, and this is neon. And I have 1 mole of neon is equal to 22.4 liters of neon. And it could be anything at STP for liters. Whenever we have liters here, we're always assuming STP. So we're always saying that this is how many liters are equal to 1 mole. So it could be neon, it could be any other gas, bromine, chlorine, it could be any substance, 22.4 liters. Moles go away, and we end up with, I believe, 165.98 liters of neon. How many moles of barium chlorate are in 2.14 times 10 to the 24th molecules, right? Molecules is a particle number amount, right? And anytime I have a particle number amount, I know that I have to deal with Avogadro's number, which is this many of those particles are equal to 1 mole, right? So that's my conversion when I'm dealing with a number amount of something. And you'll have all of these provided for you. But since molecules is what I'm provided, I'm just going to substitute P for particles just to simplify this. So that's 2.14 times 10 to the 24th particles of barium chlorate. And set up our table or your factor label. I know that there are 6.02 times 10 to the 23rd particles of this barium chlorate in 1 mole of that. All right. So remember, our mole is kind of like the bridge unit. That's why moles are such a big deal in chemistry, because it allows us to bridge things like particles and number in counting to liters, say, or to grams, right? So that's the whole idea behind that mole value. So particles or molecules, whatever you kept it as, go away. And now I'm going to do this one for you in the... Hello, that's Spotify. We don't want Spotify. We want this. I wouldn't mind some music right now, though. So remember when you have these scientific notation values, you want to use parentheses. So 2.14. You could do this one of 2 ways. You could do times 10 to the 24th. But you got to make sure that you reset that parentheses. Or what I think is easier for most of these calculators, again, you could also do like just make that a 10. You could use the caret, and you could say 24, right? So you could do this a bunch of ways. The way I like to do it, that's easiest for me, is 2.14 second. And wherever you have these 2 capital E's, that's basically what 10 times 10 to the whatever is. That's what that means there. So I could just say 24 now. All right. So E right there represents that. And then close parentheses. And I'm dividing by 6.02 times 10 to the 23rd. All right. Now that gives me 3.55 and it was moles of, and that was barium chlorate. All right, now, if you did not do that, so let's say we do 2.14, and we do the same thing, but we don't use parentheses, chances are your calculator, I don't know about this calculator, but chances are your calculator's kind of going to mess it up. This one doesn't. It takes into account that value. Let's do it one more way. This is not anything you have to worry about. I just am curious for my own wonderment. But 6.02 times 10 to the 23rd. And now, see, that's what I was getting at. So the calculator function recognizes the E as the times 10 to the, but if you were to just do it like this, right there, where I just highlighted it, it's not, the calculator is not going to understand that the times 10 to the 23 at the end for 6.02 is with that 6.02 number. And that's why it's so important to make sure that you put parentheses no matter what, all right, for each of those. So I just wanted to show that again. All right, and the last one for this part, again, remember STP just means standard temperature and pressure. And then how many molecules are there in this many liters of nitrogen gas? And remember, diatomic just means that nitrogen, like a couple of others in Honkelbrief, are diatomic, which means we have 2 of them for everything. So how many molecules there are there? Well, let's replace that with particles again. So we're talking about particle amount. Here's 3.56 liters of nitrogen gas. And we end up with needing to convert to moles, as we tend to do if we need to go to different units. We know that 22.4 liters of anything are equal to 1 mole at STP. And then since I'm in moles, now I can take moles and I can convert that to particles, which I know my conversion for that is Avogadro's number. So moles go away. As you can see, anything that's diagonal is going to cancel out. I'm left with what I want in the end. Up there at the top, particles of N2 is my unit, and I have 9.85 times 10 to the 22nd particles of nitrogen gas or molecules, because it's a group. So that's part 1, and look forward for part 2 coming soon.